I am a student with Dr. Cardenas. Today I'll be presenting one of my posters at APM about improving TG263 compliance using locally hosted large language models. It's a collaboration I did with Rex, and you heard a little bit about this from Drew earlier. But effectively, TG263 just tells us how should we be naming things. So if we ask physician A and physician B, how would you name this target? There's a good chance they're not going to agree on what the exact correct name should be. You can see kind of a list of different names there. And so the idea is if we ever want to go back and retrospectively look at a specific site or a specific kind of target, it becomes very difficult for us to understand which kind of targets are the same and which ones are different. So for us, consolidating and making sure that there's good agreement inter-physician and physicist and whoever else is on the clinical team, getting them to agree on a good name is difficult. So consolidating this using large language models is kind of the output of this study. Now the way we did it was we would have the initial so-called incorrect name. In this case, we're using example GTV_6th_rib_R. So we asked the LLM to make a description of what they think the radiation oncologist was meaning to say in this specific context. So in this context, it would say the gross tumor volume is located on the 6th rib and the laterality is the right side. And then from that description, we can then extract certain metrics or certain qualities about that specific name. So we can say what target type, what dose level, what's the fraction count, what's a crop away from the body, all of these other things that TG263 very specifically prescribes. And once we have this big list of qualities about that initial incorrect name, but now obviously corrected, we can pass that through to the validator that Drew was presenting earlier, that Dr. Carden built. And what that allows us to do is using that backend, generate a TG263 compliant name. So you can always go from an incorrect name to a compliant name. Now the issue is not all compliant names are built the same. We can have a name that's compliant that doesn't necessarily reflect what the initial physician meaning was. So I'll give you an example here. The PTV_RT space femur is not correct in accordance with the TG263 requirements. PTV_femurs is correct under TG263, but as you can see, it misses out the laterality information of RT, which is right in this case. Now we looked at the description and said it was PTV radiation therapy, which is, I guess you can say, reasonable for the LLM to say, but we obviously know in this context that it means right. So in this case, all of our outputs were compliant, but they didn't always match the initial contextual information that the physician gave. So this is something we're still exploring. We think we have a good couple of solutions for that. So the conclusions are we were able to get a pretty good average correction rate across 1,000 sample structures that we took from here at UAB that weren't previously compliant. It took about 89 seconds if we used a single model approach. Using a mixture of prompting experts, we got around 22 seconds per correction. So we're trying to drive that down, really build a C# tool that can sit natively right where the physician's naming it and provide those corrections in real time. So that's the first one.
Now, is that the same tool that Drew presented or still?
So this uses that tool to generate the name, but in order to generate that list of JSON attributes about that name, that's all LLM based, and then it'll just feed it to that tool that Drew's talking about.
You got one more?